Hello everyone, today I am going to discuss about Rolle's theorem. So what Rolle's theorem states? If f is a function satisfying the three conditions, number one, f is continuous on the closed interval a comma b, number two, f is differentiable on the open interval a comma b, and the third condition is the value of f at the point a is equal to the value of f at the point b. That means if a real valued function f satisfying these three conditions, then Rolle's theorem says that there must exist at least one point C which is lying between open interval a comma b such that f dash c equal to 0. So this is the statement of Rolle's theorem. Basically, Rolle's theorem talks about the root of the derivative function. Since here f dash c equal to 0, that means that c is the root of the derivative function. We also know that if the derivative of a function f at a point x0 is equal to 0, that means the tangents at the point x0 is parallel to the x-axis. Since here f dash c equal to 0, that means the tangent at the point C is parallel to the x-axis. Now we talk about the geometrical representation of Rolle's theorem. So there are basically two cases arise. Case 1, f is constant function. Case 2, f is non-constant function. Now first we discuss about case 1. Let f is constant function. Suppose f of x equal to for some constant k. We define f on the closed interval a comma b. Now if we draw the figure of f, then it will look like this. This is my x-axis, this is y-axis, and let a be a point here and b is another point lying on the x-axis. Since f is constant, then the value of f at the point a is equal to k. Let's suppose f of a equal to k, and the value of f at the point b is also k, since f is constant function. Now if we draw the figure of f on the domain closed interval a comma b, then it will look like this. Clearly this function is parallel to the x-axis. Now we claim that this function f satisfies all the three conditions of the Rolle's theorem. Why this is so? Because we know that all the constant functions are continuous function over the real line R. Similarly, all the constant functions are differentiable function over the real line R. That means f is continuous on the closed interval a comma b and f is differentiable on the open interval a comma b. Thus, f satisfies the upper two conditions of the Rolle's theorem. We also claim that f satisfies the last condition of the Rolle's theorem, because here we can see that the value of f at the point a is equal to k and the value of f at the point b is also k. Therefore, we can write fa equal to fb. That means f satisfies the last condition of the Rolle's theorem. So according to the Rolle's theorem, there must be exist a point C on the open interval a comma b such that f dash c equal to 0. So how can we show that? Since we know that derivative of a constant function is always 0 for all x belongs to open interval a comma b. This means that there are infinitely many C's lying between open interval a comma b such that f dash c equal to 0. Getting my point? Therefore, in case 1, Rolle's theorem true. Now we discuss about case 2. Let f is a function which is non-constant and f satisfies all the three conditions of the Rolle's theorem. Then, if we draw the figure of f, then it will look like this. Suppose this is x-axis and this is y-axis, and A is the point here and B is another point lying on the x-axis. Since f satisfies all the three conditions of the Rolle's theorem, then the value of f at the point A and the value of f at the point B both are same. Since f is non-constant, that means it will look like this. Therefore, in this graph, we get 2 points. Suppose it is C1 and it is another point C2. And if we draw the tangent at C1 and C2 respectively, then we will get these two tangents. Clearly, these two tangents are parallel to the x-axis. That means in case 2, Rolle's theorem again proved. Now we try to solve some questions based on the Rolle's theorem. Question 1. In fact, this is a question which is come in JEE Main. If 2a plus 3b plus 6c equal to 0, then show that the equation ax square plus bx plus c equal to 0 has at least one real root between 0 and 1. So how can we show that? We know that Rolle's theorem talks about the root of the derivative function. But here we have to find the root of this equation. So how can we proceed? Let small f of x equal to ax square plus bx plus c. Therefore, we have to find a root of this equation which lying between 0 and 1. So, in order to find the root, we have to construct another function capital F of x such that the derivative of the capital F of x is equal to small f of x. So, how can we find capital F of x? Simple. We have to integrate this small f of x with respect to x. Now, if we put the value of small f of x by this, we will get ax square plus bx plus c into dx. Further integrating, we can write ax cube upon 3 plus bx square upon 2 plus 6. Therefore, this is my capital F of x. Since it is clear that capital F of x is a polynomial of x with real coefficients, and we know that polynomials of real coefficients are continuous function as well as differentiable function over the real line. That means here capital F of x is continuous on the closed interval 0, 1 and also differentiable on the open interval 0, 1. Now we wish to show that f satisfies all the three conditions of the Rolle's theorem. In order to prove that, we have to find f of 0. Clearly, if we replace x by 0, then it will become exactly 0. Now, if we calculate the value of f of 1, then it will become, if we replace x by 1, then it will become a by 3, b by 2 plus c. Further calculating this, we can write 6 2a plus 3b plus 6c. Now the condition is given like this. So putting the value here, we can write 0 by 6, that is 0. Therefore, we will get f0 equal to f1. Both are equal to 0. That means capital F of x satisfying all the three conditions of the Rolle's theorem. So according to the Rolle's theorem, there must exist a point C naught which is belonging to the open interval 0, 1 such that capital F dash C naught equal to 0. Since capital F dash x equal to small f of x, which implies that capital F dash C naught is equal to small f of C naught, and if we replace the value of capital F dash C naught here, then it will become small f of C naught equal to 0. This shows that C naught is the root of f of x equal to 0. Proved. Now we try to solve another question. Question number 2. This is also a question which is come in JEE Advanced 2020. Show that between any two roots e to the power x cos x equal to 1, there exists at least one root of e to the power x sin x minus 1 equal to 0. So how can we prove that? Solution. Given that e to the power x cos x equal to 1, let this equation has two roots. One is alpha, another is beta. And also assume that alpha is strictly less than beta. Since alpha and beta both are the roots of this equation, then both alpha and beta satisfies this equation. Therefore, you can write e to the power alpha cos alpha equal to 1 and e to the power beta cos beta equal to 1. Further calculating this, we can write cos alpha equal to e to the power minus alpha, and here we can write cos beta equal to e to the power minus beta. Further calculating this, we can write cos alpha minus e to the power minus alpha equal to 0 and cos beta minus e to the power minus beta equal to 0. We put it as equation 1 and write it as equation 2. Now we let a function f of x equal to cos x minus e to the power minus x. We know that all the trigonometric functions as well as the exponential functions are both differentiable as well as continuous over the real line R. Therefore, f is continuous as well as differentiable over the real line R. Because we know that difference between any two continuous function is again continuous and difference between any two differential function is again differentiable. Thus, we can say that f is continuous on the closed interval alpha comma beta and f is differentiable on the open interval alpha comma beta. Thus, f satisfies the first two conditions of the Rolle's theorem. Now, we also claim that f satisfies the third condition of the Rolle's theorem, because in order to prove that, we have to calculate f alpha. F alpha is basically cos alpha minus e to the power minus alpha, and now using 1 we can write this value is equal to 0. So f alpha is going to be 0. Again we calculate f beta, which is equal to cos beta minus e to the power minus beta. Since using 2, the value of cos beta minus e to the power minus beta is equal to 0. Therefore, again we can write f beta equal to 0. Thus, we will get f alpha equal to f beta equal to 0. Thus, the third condition of the Rolle's theorem again satisfied by the function small f of x. Since all the conditions of the Rolle's theorem satisfying by the function f, then there must be exist a point C which is lying between open interval alpha comma beta such that f dash c equal to 0. Now, since f of x equal to this, Now we are going to calculate f dash x from here. This will be f dash x equal to minus sin x and minus minus plus e to the power minus x. Why this is so? We know that ddx of cos x equal to minus sin x and ddx of e to the power minus x equal to minus e to the power minus x. So using these two things, we can write f dash x equal to this. So putting c in place of x, we will get f dash c. So replacing the value of f dash c, we can write minus sin c plus e to the power minus c equal to 0. Further calculating this, we can write sin c equal to e to the power minus c and e to the power plus c sin c equal to 1. Therefore, we can write e to the power c sin c minus 1 equal to 0. This means that c is the root of the equation e to the power x sin x minus 1 equal to 0. That's all. Proved. Thank you.